Okay, so moving forward regarding the additional type of statistical tests that were used, now we're going to take a minute to look at this highlighted section of the Fisher-Exact test and the chi-square. So these are two that we have not necessarily talked a great deal about, but in this case, these are two additional tests that the study or the authors of the study are using to look at and assess categorical variables. Okay, this is important to note. These two tests, a chi-square or a Fisher and or a Fisher-Exact, are used for specifically for categorical variables. So let's take a minute and let's talk about what a chi-square is. Okay, so essentially, oh, perfect page. Okay. So a chi-square is a calculation used to determine how closely the observed data fits the expected data. If the chi-square value is small, we can accept our null hypothesis. And if we remember what the null hypothesis is, that means that we don't expect change, right? However, the alternative hypothesis or the research hypothesis is that we do expect to see some change. Now, the chi-square, again, compares collected data with expected data. It's used for categorical variables only, and if it is large, we can reject the null hypothesis, and if it's small, we accept our null hypothesis. Okay? And let me see if I have an example to provide you. So the formula for chi-square is observed data subtracted by the expected data. And then you square the results and divide it by the expected data in all categories. Now to do this, we have to use, again, what we used for a t-test that you've seen previously, degrees of freedom. The degrees of freedom, again, is labeled as, I should make a note here for you. It uses D, or you'll see it as DF, and this means degrees of freedom. And similar to how we use a t-test in looking for the critical value for a t-test, you use the degrees of freedom to help you determine what your, essentially your p-value is going to be, okay? So degrees of freedom for a chi-square would be the number of categories, so n minus 1. So whatever the number of categories that the study is looking at, minus 1. And the same format follows. You will then locate your chi-square distribution table, which you can find pretty much online or anywhere. And I am going to show you an example. But using your degrees of freedom, you will locate the p-value you're interested in using for your process. And generally, as you always know, we generally fall for the 0.05. And let me just show you. Yeah, here we go. Okay. So we generally fall for the we go for the 0.05. And the same way you would use your degrees of freedom, you would follow for where well, I should say in this case, you would use your degrees of freedom based on your calculation using, okay, using the formula provided. Oh, sorry, this is an example that I was going to use. So essentially this, so if this was your observed data and this was your expected data squared divided by the 250, the answer that you get for this, you would use that knowing the degrees of freedom, and you would go all the way over until you found your exact p-value. Okay? And that's where you make your decision if you should reject or accept the null hypothesis. Let's go back to that picture that I had with the numbers in it. We're going to use this as an example. Okay, so let's just for sake say that we're looking at applicants who are applying for Concordia's occupational therapy program, okay? And let's say those who applied for there's a number who applied for the program that didn't get in. So using just these numbers, and these aren't any real numbers, so they're not correlated to anything. I just pulled them to make a fake scenario. But let's say our research question is, if we expect that half of the students who apply for the program get in, is there a difference between our expectation and the observed? So if we expected half of our applicants to get in, then the mean we expect would be, or 250. So we expect 250 to get in. So our formula would be 200. So let's just say 200 were the students that actually got in, okay? But we expected 250 to get in. So this is our observed, this is our expected. So we observed 200 students get into the program, but we expected 250 students to get into the program. Now, using our formula, okay, the answer to this should be 200 minus 250 squared divided, should be 10. Okay, so the answer of this should be 10. Now, using our degrees of freedom or our chi-square distribution, we know that there are only two categories for this study. I'm sorry, two categories for this study. Students either got into the program or students did not get into the program. So we also know that for degrees of freedom, our formula is n minus 1. Number of categories minus 1. So in this case, our degrees of freedom is 1. That's how much room we have to vary, okay, is 1. 1 degree of freedom. So using this 1 degree of freedom and expecting or using a level of significance of 0.05, because again, that's generally what we'll use, you going from 1 degree of freedom all the way over to 0.05, we expect that the p-value should be 3.84, okay? After completion of our statistical test, right? Oh, sorry, I'm trying to go back. We determined it was 10. So in this case, 10 is higher than the 3.4. So in that case, that would mean that, sorry, let me go back to chi-square here. If the chi-square is large, we can reject the null hypothesis because the 10 is higher than 3.84, which is the p-value. So in that case, we know that this should be statistically significant. Now, there will be cases, right? If the scores are close or basically the same. So let's say we had different numbers, right? And let's go back to the chi-square chart. Let's say we had different numbers and or whatever the case was, we didn't come out with a 10, okay? So let's say the score was close to that 3.84, basically the same. In that case, if that had happened, we wouldn't have rejected the null hypothesis, okay? Because it's not statistically significant. So we use the number of categories for chi-square, and this is the assumption that the sample data, or we're basing it off the assumption that sample data is biased and allows shift for error. So that's why we use the chi-square chart, and that's why we use the degrees of freedom, because the degrees of freedom tell us how much room we have to vary. Okay. Now, if the score happened to be closer to another area or another data point on this chart, then we would use that p-value to report the statistical test, okay? And generally you would do that if you don't have a p-value if that makes sense. So we kind of go to mind that it should be 0.05, but if it doesn't fall near that 0.05, we know that it's not statistically significant. So you're going to use the p-value, right? You can't use 0.5 because it's not. You're going to use the p-value that it was closest to. And in that sense, that's where you get the p, right, is greater than 0.05. Okay? All right. Perfect. And that's what we use to report if it has no statistical significance. All right, now let's talk a bit about the exact Fisher, because that's also in here. Now, the exact Fisher, this actually is a similar test to the chi-square. It actually is just more accurate, but it follows the same format of using 2x2 tables, and it also only focuses on categorical data. So specifically looking at two nominal variables, okay? So we won't go into details about that, but know that they are similar tests. Therefore, they're using both, but this one is a little more accurate. What I would like to point out, something that I didn't talk about earlier, was for ANOVAs. In the article, you will see F statistics or F ratios used to report anything that was in regards to an ANOVA. Okay? Now I'm going back to my notes for you guys. Uh, Similar to a t-test, right? So you have a hypothesis test. That's our t-test, our ANOVA, our chi-square. And I have z-square in here, but we haven't talked about z-squares. But the test statistic is what's used to come up with the answer. So ANOVAs use F values, similar to the t-test use t values, which we have talked about previously. If I go to t-test, where I recently pointed out that often in a paper you will see something like this, where you're looking for the critical value. Same difference for F ratio, follows the same format, okay? And it does also use degrees of freedom, just as chi-square does, because we need to know, again, how much room do we have to vary. While chi-squares use categories, t-tests, as you know, use samples, okay? And then for ANOVAs, they use the F statistic, again, as I just mentioned, or the F value. And the F statistic is the ratio of the between group variance to the error variance, or the F test, which is used, same format, right? Is used to determine how much of the total observed variability in scores can be explained for differences among the subjects. So the F statistic is similar to the T statistics. You're looking at the ratio of between group treatment effects to within groups variability. Okay. It can also be applied to independent groups or repeated measure designs, which, as we know, this study does have, and it may also be, as we talked about, a mixed measure design. Okay. So that's just to point out a few things regarding the stats, so you're a little more comfortable with what's going on and you're able to talk about the stats. So when you're talking about the stats, you'll report what was used, and you'll be able to say if it was accurate or not. So the more we keep doing this, the more familiar you'll become with the terms, and providing you a little bit of background more each time will help you just better acquire the knowledge, and again, to become second nature. But I do just want to continue to show you how important it is to know the level of measurements and the type of variables used, right? And just as a reminder, nominal data, because I talked about the Fisher's exact, exact Fishers or Fisher's exact, focuses on two nominal variables. And as we know, that does fall under categorical data, right? It can only be people and objects that are assigned to categories based on some study criteria. So examples that I have is blood types, type of mental illness, site of hemiplegic involvement, or area code, that kind of thing. Okay? Now let's just take a quick look at the graphs to see what we're looking at here. Here you have your pre and post test fall threats, fall prevention, And then right above here, you have your table or your participant characteristics, which is your baseline characteristics. All right, thanks.